Welcome to the 19th class meeting of EECE341, Introduction to Communication Systems. We are grading, the TA and I are grading the midterm exam and found something interesting, and we are going to share some lessons today. Anyway, last time I started to talk about voluntary project and how it works. You are free to choose to submit this project report or not. There will be no penalty. Only gains will be done. And as many as of you do the final project, everybody's grade will grow up. But what is important is that you cannot say that after the final exam, I want to do a voluntary project. You can't do that. So your topic must be approved by me before final exam, before you take the final exam. No rush, final rush is allowed. The due date is, according to the academic calendar, we have the final submission of the grade on December 27th. So the voluntary project is due on the previous day. But usually I study 2 days before, but 2 days before is Christmas. So I don't want to be a Professor Scrooge. So I set the deadline as 9 a.m. on the next day of the Christmas. Anyway, there will be announcements on the classes offered in the next semester. And there are many companion courses with this course, or communications, not only communications, but also networking related courses. And last time I emphasized that there will be two more hardware oriented, but communication related courses next semester. So one is the EECE341, and the next one is EECE414. So if you are more toward the hardware oriented communications and networking, these two courses will be very, very good. I'm not going to teach, so you'll be happy. My messages are now increased to 4. So first, simplify, visualize. And the next 2 messages is that whenever you think something about it, or you discuss on a topic, usually you have to yourself at least define the terminology you are using. And whenever you define something, never forget to check the existence of what you are talking about. And if existence is not proved, then possibly or highly likely that all the following discussions will be vogue, which means that for nothing. If what you define exists, then check the uniqueness of it. Uniqueness of what you have defined is not necessary. However, to check whether it is singular or unique or it is plural is very, very important, because sometimes we assume too much on what we define. We just think that something is unique and all the others are not what I want to say, something like that. That is very, very bad. Sometimes optimal solutions may be more than one. Okay? Probably some of you have taken introductory economics course where at the last chapter you are taught game theory and multi-objective or multi-criterion optimization, where you don't have only one optimal solution. You may have, in some situations, infinitely many optimal solutions, which are mathematically speaking all equal. Single one is not better than the other, but there are more than one optimal solutions. So this is very important. Sometimes we just believe something is unique and we stick to it and we lose a lot of our valuable time to chase that is not singular. Okay, so be careful. Anyway, here goes the clarification related to problem 7 of midterm. Many of you, I have found that, use the large language model to find the answer to this question. Probably you typed in, or you just capture the problem and punched into the LLM. I also tried that. And there are many large language models that also can accept the not only the text but also the figure. It worked. So what I did was like this. So I made a short, small figure file and gave it to ChatGPT and Google Gemini, and asked to write answers for me. And what I have found is that both of the large language models generates most of you have provided as answers, and got just 2 out of 10 points. However, when I summarize like this, I have written in Korean. So as you see that there are many numbers, right? And you know that sometimes these large language models makes very stupid mistakes in just adding up and subtracting and getting something. Here, the key is that you find, or you notice, or LLM notices that the interference is above 60 hertz from the frequency of the local oscillator 2. And 60 hertz, you may say 60, maybe 50 or 30. It is not. 60 is a very alarming number, especially in the United States, in South Korea, and many countries, because it is the frequency of the AC power line. Of course, in some countries, I remember Japan has 50 hertz AC power supply, power line. However, 60 is a very special number. So I extracted that number and gave the large language models in this way. Specifically, I said the interference is 60 hertz higher than the local oscillator frequency 2. And actually not being, sorry, Gemini. Gemini provided very long answers, and there was correct answer. It listed all the possibilities, including most of you have provided, but Gemini provided. However, even though I gave it, ChatGPT failed to this problem. However, I tried other problems not appeared in the midterm exam, but sometimes ChatGPT is much, much better. And probably if you try Bing or some Perplexity or other thing, they may provide good answers. What is the lesson here then? The lesson is that don't try just putting this figure file as the input to as the prompt of the large language model. You extract some information. So some people say that it's prompt engineering, but that is very important to expand your knowledge. Okay? Sometimes these large language models may not have a simple calculation. See here, I intentionally gave all the frequencies in the unit of kilohertz. And you may easily see that this one, 0.06 kilohertz, is actually 60 hertz. But the large language models couldn't notice it. However, we can easily notice it and prompt like this, then you may have, depending on your choice of large language model, you may have something interesting, something correct. Got it? So the capability of well utilizing large language models or any AI machine learning models is also very important capability of an engineer in the new era. So you have to be well prepared, but don't be stupid. Just copying the problem and hoping that the large language model even just correctly find 0.06 kilohertz is 60 hertz so that it's related to the AC power. That is not at this point what is going to occur. So never forget to well summarize the problem and provide some essence so that you have the correct answer. By the way, only 3 students got 10 points out of 10 points. First one is Choi Moon-gyu. He drew a very good block diagram for the transmitters. And also Park Han-jun drew good spectrum domain, frequency domain figures, precisely showing what is wrong. And also, Moon Young-jin pointed this out. South Korea used 60 hertz AC power, and that is interfering, something like that. So these 3 students got 10 points out of 10 points. Anyway, so I believe you now have a good lesson. So here we are. We are still studying angle modulation and multiplexing. And many of you say that, hey, it's almost 3/4 of the semester and we are still covering chapter 4. Yes, that's what I told you in the beginning of the semester, because all the rest will be covered more in detail in the following companion courses like Introduction to Digital Communications, Introduction to Information Theory, and Introduction to Digital Signal Processing. The key you have to understand in my especially Introduction to Communication Systems is what? Complex envelope. So I will repeatedly tell you, complex envelope is what you have to understand through this first course in communications. And what is the next one? The next one is that, as I always emphasize in my courses, there are 2 big buildings in electrical engineering. The right side building, here, the engineers do the research on what? What kind of mathematical and logical operations is interesting, benefits us. And on the left side of building, these guys do the research on how to implement this one. Sometimes, since many of them are academic researchers, they ignore the level of state of the art of in the other building. So they kind of stretch too far and sometimes believe they are doing something too futuristic. However, if this is very, very, very tantalizing, so you really see that will be very good if it occurs, the other building guys make it possible. The other situation also possible. Sometimes we just think that such and such, for example, in this course, modulation scheme is good enough. And we just try to improve that one. However, the electrical engineers on the left side building makes a lot of progress. Like, for example, digital signal processing of almost all analog signal processing. In that case, we just need to change everything to digital. And suddenly, revolution occurs. So as an electrical engineer, never forget that these 2 buildings, they sometimes race towards the future. And even though you live inside one of the buildings, always try to see what's going on in the other building. That is my message. Got it? Anyway, so here goes the review of last class meeting. We studied the transmitter part, especially transmitter part of the angle modulator with emphasis on frequency modulator. And this angle modulation in nature can be classified as a nonlinear modulation. Of course, its spatial case becomes linear. However, in most of the cases, it's nonlinear modulation. So it's very hard to analyze what will happen at the output. The reason why our signals and systems course was so successful with Fourier analysis was that we assumed the system is not only linear, but also time invariant. You will see in some control courses, automatic control or some other courses, linear systems, if this is the set of linear systems, linear time invariant systems occupy a very small portion of it. Actually, linear time varying system is very important. And your Fourier analysis tool sometimes does not work well. So be careful. What you learned in signal gen systems was mostly for linear time invariant systems. However, you have to expand your knowledge to general linear time varying system, where Fourier analysis is not omnipotent. In Korea, 맞는. Okay, the Fourier analysis is not omnipotent in general linear systems theory. Anyway, so angle modulation is in nature almost every time it's nonlinear, so it's very hard to analyze what will happen at the output. So here goes angle modulator. And here goes your message. And you want to know what will happen here in the time domain, in the frequency domain. And as I told you, it's not easy. So what we do is that whenever something's very difficult, we simplify. We simplify the input message to what? Simplest signal. Here, the simplest one is a sinusoidal signal. Of course, in some cases, you have to think first about the constant signal, okay? Sometimes zero signal, but in our case, zero signal means nothing. Constant signal also means not much. That's why we have chosen some other signal, which is, in this case, single tone. Sometimes we call the signal single tone or a continuous wave. And be careful, the term CW means different thing in radar engineering or in the context, even in the communication system. So single tone means that a sinusoidal signal. Of course, here we are studying kind of early times of the communication technology. So all the message signals is real baseband signal. However, in digital communications, most of the message signals will be complex baseband signals. Anyway, so here, real baseband single tone. So which means that it is sine of something or cosine of something. Then we can do some crude analysis. And where we needed what? Bessel functions, you remember. Anyway, this simplified case can be analyzed. And here what we need to review again. But let me give you the big picture first. So in the time domain, what we do is that we notice our signal here, or at least the complex envelope of this signal is a periodic signal when we simplify the message as a sinusoidal signal. Then periodic means Fourier series. So what you do is that you use the Fourier series tool to analyze what's going on. And that gives something very interesting, right? Even though in the DSB-SC, if the message signal is a tone signal, what we will see is that here, if this is the carrier frequency, you will see two delta functions, right? Because sinusoidal signal, sine or cosine, consists of two delta functions according to the Euler's identity. In the angle modulation, even though the message is a single tone, how many direct delta functions do you see? Mathematically speaking, uncountably infinite number of delta functions you will see. Of course, not all the delta functions have very large strengths. The strength decays. So approximately, the signal is band limited. In the frequency domain, as I just told you, we have delta functions, and the bandwidth is the Carson's rule, as we will see today in depth. Carson's rule provides the idea of bandwidth, of course, very rough, approximate bandwidth of angle modulated signal. And also, we are going to see the transmitter structure in today's course. There are two types of transmitters. One is just directly using the definition of angle modulation. Especially, this is suited for frequency modulation. And second is the indirect method. And here, interestingly, we first generate narrowband FM signal. And then, by using frequency multiplier, in Korean, 주파수 채배기, during the up conversion, we make the wideband FM signal. So this is especially TX structure for FM. And you know, in especially analog modulation, FM is much preferred than phase modulation. So transmitter structure for FM is very important for you to understand. In the receiver, you will learn the device called frequency discriminator. And also, you will see a very practical structure of FM receiver that consists of frequency discriminator and envelope detector. And you will see this envelope detector appears not only in the DSB with transmitted carrier or large carrier, but also in FM receiver. Okay, so this is the big picture. So here goes a kind of pages for the review. So here, this is the signal or message signal, and here is our modulation index. So as you remember, in AM, what was the modulation index? It was a little bit complicated, but what we had was something like this. So we have, let's say, beta. Something like this. Here, Mn of t is the kind of normalized message signal so that its largest deviation from 0 is 1. Okay, so we have some assumption like this. Okay, so beta is less than 1 means that the envelope detector works well. Beta greater than 1 or envelope detector may give us some distortion. Anyway, this is the modulation index for AM. And here we do something similar. See that? We said our message signal is sinusoidal signal and intentionally limited its peak value to 1. So this corresponds to M sub n. So beta can be said the modulation index of angle modulation. So here, beta is called the modulation index of the angle modulation. Now, it's not easy to directly see that this is a periodic signal, but if you convert the signal to a complex using the complex envelope, then you can easily see that the complex envelope is a periodic signal because this is period. Actually, you can show something very general. Suppose f is any function, and you have some g, and if g satisfies periodicity condition, then what happens? This composite function is also periodic, right? Because the argument becomes the same, right? So sine function's periodicity makes this complex envelope's periodicity. And you can easily show that the period of G becomes period of A. It may not be fundamental period. Sometimes, depending on the shape of F, you may have different frequency, usually higher, but still the frequency of or period of X serves as the period of the composite function F composite G. Got it? So you can expand this complex envelope using the Fourier series. And in order to find the Fourier coefficient, you need to use the Bessel function. Since our use of this Bessel function is limited combined with the Fourier series, we do not need general definition of a Bessel function. We need some special case where this integration formula, not the differential equation. For the general definition of the Bessel functions, you need a differential equation, but for the special case, this may serve as the definition when something is integer. Anyway, we use the Bessel function of the first kind to find the Fourier coefficient. And after you plug in that Fourier coefficient, see that? This is now the Fourier series representation of our complex envelope. Then you have the Bessel function here in the real bandpass signal, right? And this nth order is related to what? The nth harmonic of your delta function. So if I draw in the frequency domain, especially the positive, then here goes the carrier frequency Fc, and here is your Fm, and here's your minus Fm, and other things. Got it? And interestingly, you have the tone at the carrier, and you have harmonics. Got it? So apparently, mathematically speaking, you have countably infinite number of delta functions. And we may worry about this phenomenon because the bandwidth is the most scarce resource in radio communication. But fortunately, if you see the shapes of the Bessel functions, if the order increases, the trend is that the value of the Bessel function decreases. So not all of these delta functions are significant. Only some are significant. And in order to check how significant they are, we need to calculate the total power of the transmitted signal and the power occupied by this carrier, and also this first and second and a few harmonic components. That's why we need in the time domain to analyze the here the power in the angle modulated signal. So what we do is that given the real valued bandpass signal of angle modulator, we compute the power. And it's very easy to compute the average power like this. And here, this second term is, sorry, is it correct? Yeah, this is dominating. So you may say that and also after averaging out, the cosine function is 0, time average of and a sinusoidal signal is just 0. So you have this is the transmit signal. And it's kind of obvious because you have what? You have magnitude or amplitude, constant amplitude signal in the time domain. So your signal, whatever message it is bounded by these two values, right? As you see here. Now, we compute the power ratio of the case component the up to case components, which means that from 0, you have -1, 1, ... and k, -k. Got it? So from the carrier frequency, you take 2k plus 1 delta functions, right? So 2k plus 1, as you see, where it is. Yeah. Got it? So you only calculate the power inside this band. And as you see that, this ratio becomes what? Of course, converges very quickly to 1, which means that the total power is confined only few of these delta functions. And here goes the table. So Carson, in the early stage of FM or angle modulation, he just took this table and looked at it carefully and found a rule of thumb. A rule of thumb is what? It's not a rule. It's just in Korea, 그런 것 같더라. Got it? So he just published his result saying that, hey, when we have a simplified sinusoidal message signal, we can say that the bandwidth of angle modulated signal is this one. So here, let me draw. Now this is frequency, and here is FC. And the bandwidth for the real passband signal is something like this. So this is B, right? And now you have what? Why you have usually 2 here? Because you have kind of symmetry, some kind of symmetry with respect to the center frequency. So here you have something, then you also have something like this, something like that. And interestingly, this is the deviation FM, as you know, right? When we have a single tone. Now, this beta plus 1. So it's like first harmonic and up to beta's harmonic, you need to take into account when you calculate the bandwidth. And what is the beta? The beta is the modulation index we used in our simplified analysis, right? So beta appears here. Now, this is start of the Carson's rule. Carson not only just found, of course, this is rule of thumb already, okay? So this equal is not equal, okay? If I were you, I will modify like this, okay? So it seems that the bandwidth of a real bandpass signal, real bandpass angle modulated signal, when we have a single tone, may be written in this way. Now he wanted to generalize, right? Wanted to generalize this analysis, this lesson from the simplified analysis to the general case. And here goes his trick. Okay, so see that in the simplified model, this is your phase deviation, right? Now, what is the corresponding P of t for general message signal? Probably you have to rely on this one again, which you used in the definition of modulation index of AM, right? Here, if this beta is this beta, then here goes your normalized message signal, where you have some constraint like this. So you divide your message signal with the largest deviation. So this normalized m sub n of t has peak value 1, right? What else? What else do we have? So here, let's think about the instantaneous frequency deviation. In order to do that, you need to differentiate this phi of t with respect to t. And in order to take the frequency in hertz, not radians per sec, you have to divide it by 2 pi. And let's see from your simplified signal model first. So what do you have? You have Fm times beta. Of course, you may have some sign change, but it doesn't matter if you choose it for the cosine. But anyway, Fm beta, right? And what is this one? In terms of this model, you have what? So this is what? This is largest frequency deviation times something like this. Or in this case, you can replace the right-hand side this way. Largest frequency deviation, max of m of t. Same, right? And here, so beta serves as what? So this beta in this line, let's focus on this one. Beta serves as what? For the simplified model, it is the modulation index, but let's see it carefully. Beta is the ratio between largest frequency deviation, instantaneous frequency deviation, divided by the message signal's frequency. And this message signal's frequency is, in general case, is related to what? This one is related to the bandwidth of the message signal. So this is related to bandwidth of message signal. And what about this? This is the largest or peak frequency deviation. So instead of using beta, that is just for simplified singleton, we define D, new parameter that corresponds to beta for the general case, and define as what in this case? Here. D is defined as the peak frequency deviation divided by bandwidth of the message. Then, as you see that, F sub m may be replaced by W, and beta replaced by D. Then what happens? D is simply FD max of m of t divided by W. And now you can replace beta with D, and you have the Carson's rule. Got it? So Carson's rule has two approximations. First one is that you approximate the signal to a single tone signal. That is the first thing. And you analyze. And then you make second approximation. Hey, it seems that the bandwidth of this simplified case is what? 2 times the quantity of beta plus 1 times the frequency of the signal. Now, let's consider general case. What is beta? Beta is the peak frequency deviation divided by bandwidth of message. Now, let's call it D for the general case. Now, what can we say? FM is the bandwidth. So this FM is replaced by W, beta replaced by D. That is Carson's rule. Got it? Isn't it simple? Yeah. So Carson's rule was so accurate, actually. And this was very important because the spectrum, the bandwidth was and has been the most valuable, most scarce resource in radio communication. You don't want a station, an FM radio station, signal interferes the other station. They wanted to have enough separation between the FM radio or angle modulated signal stations. Got it? So this contributed a lot and he got a fame. Got it? And now let's relate this Carson's rule with what we already know. Suppose D is very small. What does that mean? Peak deviation is very small. So if you remember, beta is very small. You choose beta small. And you already know that you have narrow band FM or narrow band angle modulation. You are right. If D is very small, you have narrow band angle modulated signal, and the bandwidth is just 2 times the bandwidth of the message signal, which is the same as bandwidth of AM signal, right? But if D increases, you can no longer ignore this term. Now, at the point where you cannot ignore, you have to say this signal as wideband angle modulated signal. Got it? Here goes an FM case. So again, your message is a single tone. So we consider simplified case. Got it? And here, FM modulator has carrier frequency 1 kilohertz. And the maximum deviation, the maximum deviation of the phase instantaneous frequency is 8 hertz in this case. So every unit is hertz. So see that you have 1000, and first harmonic has plus minus 8 hertz, and second harmonic has plus minus 16 hertz, right? And you have other terms. Got it? And our rule of thumb says what is the bandwidth? And our rule says 2 times, and here m of t is 5 times cosine. So this 5 serves as beta here, right? And you have this 8 here. So 96 hertz. Let's see, where is 96 hertz? So 1000 plus minus 48, right? So 48, this is 2 times 48, right? 648. Yeah. So of course, there are many other terms. The author just cut here so that it includes first, second, third, fourth, fifth, up to 6 harmonic components. Got it? Of course, there are many, but they have small, relatively small power. Got it? Okay. So we covered, yeah, most of them. And our textbook has a mixed order, but here goes why FM is more preferred than PM. And I already told about that last time. So in a singleton analysis, we just say that beta is the modulation index, and this is this provides us maximum frequency deviation. But be careful. If it is phase modulation, this is directly message signal or proportional to message signal. However, if this is an FM signal, the signal divided by FM is proportional to the message for FM. Do I have to say this? Yeah. So here, the modulation index actually becomes dependent on FM. So, sorry, F sub M. So in FM, beta diminishes if we increase the bandwidth of message. What does that mean? Here. Let's consider phase modulation and frequency modulation with the same power and same message signal. Do they have the same spectrum? Of course not. Why? Because beta is different, even with a single tone. See that? This is beta, that is beta. So when you plug in this beta value here in your formula, right? The value changes. And here, except the zeroth term, the DC term, all the other terms have something interesting. Of course, if the argument here, beta, increases, there is a trend that you have smaller and smaller value. However, it starts from here. For the large order, it slowly starts and then decreases. What does that mean? High order terms, high order harmonics are much more affected by this small value of beta. So FM actually has more confined bandwidth in some range if you carefully choose this proportionality constant. Got it? So it seems that if you input very high tone, the bandwidth must increase. And that is correct for only few terms. The high order terms diminishes much more quickly in FM, which means that FM confines the bandwidth into some level. And it's better than PM. That is one thing. And actually, that is not the reason why people loved FM over phase modulation. Actually, the reason is that it was easy to implement at their time of technology. So mathematically speaking, FM may not have some preference in theory. However, in order to implement its generalized version, angle modulation, frequency modulator was a better choice at that time. Why? Because these engineers on the left side of building successfully devised some equipment called voltage controlled oscillator. By the way, long ago, whenever I used the Wikipedia, I mostly resorted to English version because it had more information. But Korean version also was good because it was shorter, so it had better summary. So what I did was that I used the Wikipedia, like punch in voltage controlled oscillator in the Google window and enter, and find the Korean version of Wikipedia first and read it. Okay, got it. And then English version. And as you do, I had a pain in reading that article written in English. Now you can just click to translate into Korean. So here goes the voltage controlled oscillator. Interestingly, it looks like that, and its oscillation frequency is controlled by voltage input. This is exactly what we want to implement frequency modulator. The output signal's frequency proportional to or a fine function of the input signal. Isn't that good? So as far as we have voltage controlled oscillator, we don't need any other thing to generate an FM signal. Of course, in the early stage of radio communication, this voltage controlled oscillator was not that good in its performance. Its output was not what we wanted. It contained a lot of frequency deviation, frequency offset, phase noise, and those things. So actually, this is not what really used in the early stage. They used the so-called indirect method, which I referred to before. So what they did was that is indirect method. And here, what do they do is that they have narrowband frequency modulator, FM, for the FM. And it's not that difficult, as you know. What we need to do is that we generate what? We generate sine and cosine of, for example, low frequency. So, and we have some quadrature component that is, geometrically speaking, orthogonal to the in-phase component, right? So here, we use simple IQ modulator or quadrature modulator, where the in-phase component has constant and quadrature component has our message. So you may say this is M of t. And the low frequency. And then here goes something interesting. Something devised by those people on the left side of the building. They devised a component called frequency multiplier. And in Korean, it's called 주파수 채배기. And it has very complicated Chinese character like this. See that? 주파수 채배기. And you rarely see this character. But anyway, it's frequency multiplier. Precisely speaking, what it does is that it multiplies n to the phase angle of its input. So suppose that this is the phase angle of the input to the frequency multiplier. Then the output is what? N times. Output has n times of this instantaneous phase. Mathematically speaking, that is the function performed by the frequency multiplier. And there are many ways, there have been many different ways to implement this frequency multiplier. Usually, they use the nonlinear device, and nonlinearity generates a lot of harmonics, and they remove unwanted harmonics. That's one of the tricks. Anyway, this frequency multiplier, this trick of using a nonlinear device, right, made the early deployment of frequency modulator possible. Okay? Theoretically speaking, as I told you, voltage controlled oscillator is enough. However, as I told you, in theory, that is enough, right? However, current or your time of technology may not allow implementation. But there are always clever guys or hardworking guys to make this possible. So what you have to do is that you have to devise some equivalent mathematical way like this. Hey, can you make something like this frequency multiplier using some nonlinear device? And your left side building friend may say, well, that could be possible, even though I cannot still build a very precise voltage controlled oscillator. Got it? So you have the output of the frequency multiplier like this. And then what do? This F0 times n may not be still high enough for your carrier frequency. In that case, you know what to do. You just use local oscillator and mixer and following high side tuning bandpass filter, or if you want low side tuning. So here goes the bandpass filter, highly likely for high side tuning or upper side tuning. Because here in the frequency domain, what you have is what? This is the NF0 times a plus IF2, and you have some signals. Just a second. Something like this, got it? So here, this is NFC, got it? So you may want to just filter out the low side part, got it? So you see now that those idea of two-stage up converter appears again and again and again. And as I told you, that was the most significant contribution of the inventor of wireless voice, the Dr. not doctor, he was not doctor actually, the inventor Reginald Fessenden. Anyway, so you see that even though new technology has come, people still reuse old technology. So it's kind of evolution. All the revolution includes evolution. All the breakthrough includes evolution. Improvement, little by little. Got it? So this narrowband to wideband conversion made the FM modulator possible in the early stage of radio communication. Now, we have to talk about demodulation of angle modulated signal, and it requires something, actually a lot. Before covering that, let me see whether I have something missing or not. Yeah, you can read this page 23 and 22. Yeah, you read it yourself. Have I missed something? Let me go up and see. So I talked about this direct method using voltage controlled oscillator and the indirect method using frequency multiplier. Yeah, it seems I've covered all of that. So now let's talk about the receiver. So first we approach the design mathematically. So here is the angle modulated signal. And this contains the message in the form of a affine function, or its derivative is an affine function of the message in PM and FM respectively. And the problem is that this is the input up to the power amplifier in the transmitter. And power amplifier not only amplifies the input signal, but also distorts it, because power amplifier is a nonlinear device. Usually, power amplifier has output power versus input power in this form, which means that this slope is very large, much bigger than 1, so that it can amplify a lot. For example, 1 milliwatt signal becomes 1 watt signal, or a few kilowatt signal, which means that this slope is 1,000 or 10,000 or something, right? Yeah. Even though I just draw a line with little bit looking smaller slope. The problem is that if your signal power becomes large, your gain reduces. Some amplifier even have peak, depending on the technology used to implement it. The problem is that these amplifiers have power efficiency increases usually as your operation point becomes closer to this nonlinear region. So there is a dilemma, okay? You want to best utilize your power amplifier. Then you have to drive it at the near maximum capability. But it introduces nonlinear distortion. And whenever you have a nonlinear something, it's hard to analyze, which means that we don't predict what will happen at the output precisely. It's very hard in general. One bad thing about AM is that the message is conveyed by the amplitude of the signal, right? So if you have distortion in the amplitude, which is related to the distortion of this power, then you lose a lot of information. But good thing for angle modulation, or especially frequency modulation, is that it has constant envelope. Of course, there is distortion. However, the AM may operate this way. This is the average power, and your signal may vary this wide. But FM may operate here because, as you see, that the power is almost fixed, right? So FM may operate here. AM must operate here with lower power efficiency. Right? So that's why many people love so-called constant envelope waveform, which means that your real valued bandpass signal has complex envelope whose modulus absolute value is constant for all t. Here for all t means for large enough time span, right? This is constant, and because this is the definition of envelope, right? Envelope of the signal. So constant envelope. The problem is that this is mathematically good, but we need something more. Continuous phase continuity. Suppose you have a cosine function whose phase angle abruptly changes. Then what will happen? As you've seen from the comparison between PM and FM, you may have something like this. Do you see? This is a sine part, and this is cosine and sine. Mathematically speaking, is this signal? So let me see, this is the real part, okay? And you have imaginary part, okay? This signal have constant envelope. However, it does not have continuity in phase. And this discontinuity in phase actually applied to the power amplifier, real world power amplifier, you have distortion. Got it? So in practice, we not only need continuity, the constant envelopeness or envelopes constantness, we need continuity in phase. One good thing is that frequency modulation satisfies this one. Even though you have abrupt change in the message. Do you remember the figure? So let me go up. Where it is? Where is our comparison between two signals? Yeah, here, do you see? So suppose this is the message and you have abrupt change, right? Now, output of phase modulator has phase discontinuity. However, you see the frequency modulator, it has phase continuity. So FM is in many aspects better than actually phase modulation. Got it? So there were many reasons why people used FM over PM in the early stage. Of course, the most important reason was the easiness in implementation. That's what I believe. Okay. However, as I told you, there are many other reasons why FM is preferred than PM. But be careful. In this time of digital communication, in this age, your age, the lesson from the reason why it was true in the old age may no longer be true. Got it? Currently, interestingly, many waveforms for your Wi-Fi, for your mobile telephone, they rarely employ frequency modulation. You see that? AM, I will explain later, amplitude modulation was a breakthrough for wireless voice. However, it had a lot of weakness. That's why people try to develop new ideas. And FM was a very good idea at that time. And at that time, at the state-of-art implementation technology at that time would support that. However, now we are living in digital era. What does that mean? Almost every possible, mathematically possible operations can now be implemented. For example, when I was at your age, when I said to some people saying that I want to sub-major artificial intelligence, especially natural language processing something, everybody recommended me not to major in that. That's one of the reasons why I chose communications. At that time, it was impossible to compute this fast. It was impossible to handle this large language model. So people just used different models, smaller model, handcrafted, and that didn't work very well. Of course, it made a lot of progress at that time using, for example, hidden Markov model or something. So never forget, okay? Something mathematically possible could be, it may take a lot of time, but could be, someday will be implemented in real time. That time may come too early. I never imagined this world, this year 2024 will ever come in my life. I never imagined. At your age, my friend majoring communications said what? Hey, doing singular value decomposition 1,000 times per second, impossible. Now you can do that very easily. Can you believe that? So even though I explain why FM was adopted, that is old story. So you always have to work with your friend in other building. Got it? That is my message. Never forget that. Okay, now here goes the mathematical mathematical idea. So right side building idea of how to demodulate AM signal. So as I just told you, this is the transmitted signal. And even though there is distortion due to the nonlinear power amplifier, FM is more robust to this distortion. So let's assume for simplicity that our received signal is just attenuated and delayed version of our input to the power amplifier. Okay. So here you usually have pre-selection filter and low noise amplifier. And here, this is just attenuated, so gain or and delayed version. But to make everything simple again, let's assume that the output of our low noise amplifier is same as our input to the power amplifier in the transmitter. So as I told you, we make a simplification again and again and again. So our received signal is something like this. Now, we want to develop some mathematical procedure to extract this phi of t or derivative of phi of t. What do we do? Anybody? So what do we do? One idea is like this. What if we differentiate this signal? So you know how to differentiate this function of time t, right? Do you know? So cosine, let's say, what is the derivative of this one? Is it negative sign? Am I correct? What about this composite function? You have negative sine g of x times g prime of x, right? That is Leibniz rule, simplest form. So we need to differentiate this. Okay? That's good because if we differentiate that one, we have something. So interestingly, if we can differentiate our received signal, then what happens? We have some constant plus derivative of instantaneous phase, which is what? Instantaneous frequency deviation. And in FM, this is directly proportional to our message. So let's rewrite this one. Let's rewrite this one using the complex envelope idea. Anybody? So this is negative real part, right? So you may say that 0 plus j Am I right? So here you have negative and sine something. So you can put this one here in the pure imaginary part. And you have e to the j2 pi fct. And you have e to the j phi of t. Am I right? So this is the complex envelope. Now, mathematically speaking, what if you can apply envelope detector, mathematically precise envelope detector to this signal? You have this one modulus. And e to the j phi of t disappears because it's constant modulus signal, right? Now, what is the modulus of this one? You have absolute value of FC. So if FC, 2 pi FC is large enough, what is this one? It looks similar to something you've seen already in AM, right? In AM, if the modulation index beta is chosen smaller than 1, what happened? You have DC and your message. Same thing happens. Got it? Be careful. Almost zero textbook in the world explains the mathematical idea of FM demodulation in my way, okay? You are learning in the most unique way in the world. Got it? That's all for today.